All right, welcome to The Explainer. Today we've got a real technical whodunit for you. We're going to look at how one tiny, almost invisible detail managed to cause a massive, and I mean really expensive, industrial failure. So let's get into it.
Okay, just look at this picture. What you're seeing are the main power terminals from inside a really complex, multi-million-dollar machine. I mean, we're talking melted metal, totally scorched insulation, just complete and utter catastrophic damage. So the big question is, what on earth could cause a meltdown this bad? Well, the answer is way smaller and simpler than you're probably imagining.
All right, part one. Let's head right to the scene of the crime, so to speak. Because it's pretty obvious this is a lot more than just a busted part. So here it is. This is the spindle drive unit from an Okuma CNC lathe. You can think of it as the electronic muscle that powers the whole machine. And look at the bottom there. Those massive power cables didn't just come loose. They've literally melted down. And that brought this super critical production machine to a screeching, dead halt. And get this, before anyone even really figured out what went wrong, there was an immediate price tag. The team's chat logs show they had to order a replacement exchange unit right away. The cost? $5,590. Bam, just like that. And that's just for the part. That doesn't even touch the cost of downtime or the labor to fix it. Okay, next up. Here's where it gets interesting. Before all that fire and melting, the machine was actually trying to warn everybody that something was seriously wrong. It left behind a trail of digital breadcrumbs, and now we're going to follow them. So check this out. The machine gave two critical clues right on its screen. On the left, you've got this general exception alarm. But on the right, that's the good stuff, the diagnostic screen with way more detail. You have to think of these alarms as the machine's last words before it failed. They're absolutely crucial clues for anyone trying to figure this out. And this is the key, right here. Alarm number 13, IPM protective function activated. So what's an IPM? It stands for Intelligent Power Module, and it's basically the electronic heart of the exact part that burned up. The machine was literally pointing a finger at the problem area, telling the team precisely where to look, long before any smoke showed up. So, this digital clue brings us to the most critical part of this whole story, the human element. This is where we see a classic showdown, jumping to a conclusion versus doing a real, proper investigation to find the root cause. And here's the first reaction from Adam, the technician on site. He says, "We assume the drive is bad as it is burnt." And you know what? That makes total sense. Right? You see a burnt-up part, you assume the part failed. It's a completely logical first thought. But was it the real problem, the first domino to fall? But then, you've got the remote expert, Fabian, who jumps in with a totally different angle. He doesn't even ask about the drive. Instead, he asks about the maintenance plan. He's asking, do you check the connections in the cabinets? Do you know the specific torque settings for the bolts? See the difference? He's completely ignoring the symptom, the burnt drive, and going straight for the root cause. And this right here, this is the expert mindset in action. Before he's willing to blame the drive itself, Fabian's running through a mental checklist of all the usual suspects. Could it be a loose connection, a short circuit, maybe the insulation failed, or the cooling system wasn't working? His questions hinted at it, but you've got to rule all these other things out before you just replace the expensive part. And it turns out, Fabian's focus on that loose connection was bang on the money. So now, let's get into the science of it. How does something so small, a tiny oversight, snowball into a complete and total meltdown? And there it is, the smoking gun. When you look closely at the fried terminals, you see the real culprit. It wasn't some complex failure in the power module. It wasn't the motor. Nope. This entire disaster started with one simple thing. A loose connection. A single bolt that just wasn't tightened down correctly. That one loose bolt kicked off a nasty chain reaction, a vicious cycle that has a name: thermal runaway. It's actually a pretty simple idea. Basically, it's when an increase in heat creates a change that, well, causes even more heat. It just feeds on itself, spiraling faster and faster, until something gives, melts, or, catches fire. The physics behind this whole mess actually comes down to this simple formula. Now, don't worry, there's no test, we're not going to do the math, but the concept is everything. It says that power, which in our case is heat, is the current squared times the resistance. A loose connection is just a small spot of high resistance. But here's the kicker. Because the current is squared, even a tiny increase in that resistance creates a huge jump in heat. It's an exponential problem. So let's walk through the play-by-play of this disaster. Step 1, a bolt is loose. That creates a little point of high resistance. Step 2, as all that electrical current tries to push through, that spot gets hot. Step 3, the heat makes the metal start to oxidize, basically to rust or corrode, and that makes the resistance even higher. You see where this is going? Step 4, more resistance means way more heat, which makes it corrode even faster. And step 5, this cycle just repeats and accelerates until that single point gets so unbelievably hot that it just melts the terminals, the plastic, everything. It's a complete cascade to catastrophe, all from one loose bolt. Okay, so mystery solved. We know what happened, but honestly, the most important part of any breakdown like this is figuring out how to learn from it. How do you make sure this $5,000+ disaster never, ever happens again? The answer, it turns out, starts with just one thing: precision. After the new part was in, Fabian, the expert, asked a super important question: what torque you applied to the bolts. The team came back and confirmed 81 Newton meters. That's about 60 foot-pounds. The key here is that it's not just nice and tight, it's a specific number, the correct manufacturer-specified number. That one little detail is the key to making sure this doesn't happen again. This led to a big change in their whole maintenance strategy. The old plan was just to check the connections once a year, based on the calendar. But the expert recommended something much smarter. The new plan? Check the torque every 2,000 operating hours. This is huge. It means maintenance is now based on how much the machine has actually been used, not just how many days have gone by. And this is really what a modern, solid maintenance plan looks like. It's not just doing one thing. It's a whole package. You've got regular visual checks. You're using tools like thermal imaging cameras to literally see hot spots before they become a problem, and you're physically putting a torque wrench on critical connections. And all of it is scheduled based on actual usage conditions. So let's just wrap it up with this thought. A single loose connection caused a chain reaction that cost over $5,000 and took a critical machine offline. It kind of makes you stop and think, right? What are the loose connections in your own workflow, in your own projects? And what's the potential cost? Not just in money, but in time and frustration, if you don't take a second to check them.